Well, I'm here at F&ME Consultants with Glynn Ellen, and we're here in Columbia, South Carolina. Glynn, how long have you been here?
I've worked for F&ME for 33 years.
Okay, and how did you get into the field?
A friend of mine got me when I was living in Florida to work as a helper on a drill rig, and that's where it started. I was a helper on a drill rig. I moved back up here to South Carolina and ended up applying at F&ME in 1989, and they hired me as a technician, and I've been here ever since and kind of moved through the ranks to the point where I run the environmental group.
Okay. Well, what does F&ME do?
We're a geotechnical, environmental and materials testing firm with a construction services test during construction of building. We're in our lab right now that does soils and materials testing. We test concrete, asphalt, soils, and to understand soils that they're going to use during construction. But we're an engineering firm primarily. We added an arm of environmental work back in the early 90s, and I've been working in the environmental realm, looking at asbestos and lead and mold and leaking underground storage tanks that leak gasoline in the ground and mold. I handle the environmental side of what the company does. And then we've got a whole group of people in this facility running all kinds of lab testing on soils and materials. We test steel, we pull steel, we've got machines to break steel on one side of the lab, and we've got machines that break concrete, test cylinders that we test to understand the strength of concrete. So that's pretty much what we do. We're an engineering firm. We do geotechnical drilling. We've got about 4 or 5 drill rigs now that do borings in the ground to understand what's there when they're going to build a bridge.
And what is asbestos?
Asbestos is a mineral that's actually mined out of the ground that it goes back to years back, thousands of years. It's a high strength, fire resistant material.
What do you like about your work? Well,
I like the work because I've been doing it a long time, and it's just kind of grown into a job that I've been one for. Talk about F&ME is a family-based thinking company. We're a really good family company. Have been for a long time. I've been here. I know everybody, and I've grown a lot. I was a technician who really didn't know a lot. A lot of the young people that come here maybe don't have engineering degrees backgrounds. Some of these people just had a little bit of construction experience, and then somehow figured out a way to get in here. Some have gone to school and are working through internships. It's grown into a company that I feel like I'm a part of.
I have Teresa here with us as well. How long have you worked with F&ME?
I started in January.
January?
Actually on an intern period right now.
Okay.
I just finished at Tech in December in the Civil Engineering Technology program.
Oh.
And so it led me to, my background's in land surveying, and I was a project manager. But I didn't realize all of the aspects to that. And once I got into Tech and was doing like the different classes and stuff, I really liked learning the soil mechanics.
Okay.
And the testing of concrete and steel, and just it's so much more to it than what you think when you think about civil engineering. You think it's just building.
Right.
And there's a lot more aspects to it. I guess different sections to it.
Yeah, people's eyes get open the more we do in this field. You know, I was just a guy learning how to work a drill rig in the beginning, and then I became a technician. And like you said, once you start testing in the field and seeing how they build structures and how it's important to know what you're putting things on top of and what the soil situation is underneath, it became fun. And I was a rock collector. I used to collect rocks when I was young, so soil became really fun for me.
Right.
So it's a pretty cool job. It's a really interesting place to work.
I would recommend actually getting into the program, because you don't actually have to be a civil engineer.
Okay.
You have I have an associate degree.
Right
now. I mean, I have other degrees. You never told to go back and learn.
Okay.
But if you're looking to get your foot in the door and a good company, that's a good place to start.
Millen Tech.
Yes.
And how long did it take to complete the program?
Me was a little less than 2 years because I had classes already. So,
great.
But they have a 2+2 program.
Okay.
If you want to get your engineering degree, you can go there 2 years and transfer to USC.
Okay.
I would go check it out. They're their building is like a silver bead building, so they're like on green environmental.
Right.
So it's very industrial looking. It's a pretty cool building.
Hey everybody, my name's Alex Abernathy. I'm the production manager here at the lab. Give you guys background. I actually transferred from Midlands back to Carolina, and I got my bachelor's degree there. It's not a requirement to be in my position. In fact, really in this lab, if you have a high school diploma, you are qualified to work here. So, anywho, or GED, you know, basically if you have basic skills, you can work in the lab. So anyway, we have a lot of ovens where we're either burning all the water out of a soil sample, evaporating it. We also have ovens that mimic air drying a sample. Not a whole lot over here. We've got a big workspace. You can see they're setting up some bulk samples for us to get tested. These stone samples down here we have on the end are actually from malfunction junction. This is some coarse aggregate testing we're doing for malfunction junction that are pending awaiting completion. Over here we've got a Marianne shaker. So this is where we essentially perform sieve analysis for materials. We pop something in there and it mimics you smacking a pan and sieving it manually, except you don't have to go through it.
Can you describe what malfunction junction is for people not from here?
Malfunction junction, aka Carolina Crossroads. It is the interchange for it's just west of Columbia, and it's going to be I-20, I-26, and I-126.
Right.
It's called malfunction junction because, as you can imagine, it's quite a cluster for traffic. So
yes,
that's a project that we are undertaking, and we are actually we're part of a new program on that, which is called we're part of the OBF team. So what's happening here is the materials are not being brought to the SCDOT's lab for testing. We actually are acting on behalf of the SCDOT as their lab.
And that's the Department of Transportation.
Yes, ma'am.
Yeah.
So instead of they're reaching out to consultants. It's a new program, a new approach to testing. So instead of, they actually incorporate statistics. So it used to be back in the day, the state would test about 10% of what, you know, the contractor's doing. Well, now what they do is they actually analyze it. And if both labs are statistically aligning, they actually can back off from that 10% in order to save money, basically saying, hey, look, this is aligning. There's no need for us to have this high frequency of it. And also the opposite of it, if the two samples are not aligning, then they will jack up the frequency of it. So it's a new program, nice to get started. What we're seeing here is pretty much 57 states. This is the coarse aggregate that's incorporated into concrete. So when you see concrete, it consists of water, cement, and fine aggregate and coarse aggregate, so sand and then this stuff. Next time you see something chipped off from concrete, you may notice large aggregate, and we're just making sure it meets the recipe designation. So, cool, yeah, I guess we'll keep walking around. Over here is where we have a lot of our asphalt testing equipment. Here we have our high-end ignition oven. We burn things of upwards of 1,000 degrees centigrade in some of these, but this is the area where we'll reduce aggregate. We also run a lot of our asphalt testing here. That's just one portion of the lab. It's very nice to have. So over here, we're still in the process. We just moved in January. You guys are not a big deal. You guys are in the process of still getting some stuff together. So kind of ignore our mess over here. But if we're circling back around, we're just getting even more ovens that we have. Back in the day, I'd say back in the day, a few years ago, we had these two ovens. This was what we operated our lab off of, the high heat, the low heat. And as you guys can imagine, due to capacity, we now have ovens that can withstand probably 4 to 5 times the amount of sand. So, but we still keep our old trusty, rusty ones. A lot of our sieves, various equipment is kept down there. What you see here that Aaron is actually doing, he's running a standard proctor. So I'm sure everybody is always, or most people have seen a sandcastle, seen it get molded. If it's really dry, when you remove the mold, it falls apart. If it's really wet and you remove the mold, it falls apart. So there's always a sweet spot for when you densify a material to where it's in its optimum form. So that's what's happening here is he's basically compacting a specimen, getting a weight, recompacting it, and finding out what that perfect spot for the sand is for when they go in the field to perform density testing. A few other things. So if we head over here, you guys may have seen some of the CBRs being molded here earlier. So this is our CBR tank room. CBR stands for California Bearing Ratio Test. Essentially what we're doing is trying to define how good a soil would act as a subgrade underneath the pavement. So we're compacting it, exposing it, saturating it for 4 days, and then we actually apply load to see how it's resistant to support a pavement. So that's what we have going on in here. Fortunately, we have a room designated to it now. And it's a lot. Yeah.
We've just moved here, by the way. We've grown as a company, and this is a new lab getting set up and still operating. But as a company, we've just moved into this building, so I'm seeing things that we've got now that we haven't ever had in the 33 years I've been.
Dually giving Glynn a tour.
Yeah, I'm getting a tour too.
What do the ovens do? Like, I know they're heating samples.
So the ovens, there's a lot of applications to it. The most common one is something that's moisture content. So if you have soil, how wet is that soil? How do you define it? And basically, it's the proportion of the amount of wet soil, water or moisture inside of the soil, proportion of that over its dry soil weight. So just like he's running on here, you can basically put it in there, you put the sample in, you weigh it before it goes in the oven, then after. And the difference in weight before and after is basically the water that evaporates. And we can use that as a calculation to determine moisture content for it. But there's a lot of different things. If we're trying to run, say for instance, we do want to run the sandcastle test, like I said, and see how dense the material is. If it's too wet, if you're already past that optimal point where you're too wet as material, you want to dry it out. So that's where the low heat oven comes into play. We actually mimic, if you were to just sit a pan out and it sits there for a month, it air dries inevitably. And that's what we're trying to mimic there. So there's a lot of purposes for it, but that's the most common application is initial drying for sample setup. And then additionally to get moisture content from samples.
And what could happen if none of this went on before starting to build or, put a piece of cement on soil? What could happen?
Yeah, you could be building, settlement. You could say, for instance, if they build a road on something that they shouldn't build a road on, I'm sure you guys see potholes, cracks.
Okay.
A lot of times the cracks that can come from the top of the asphalt may be derived from the asphalt, but if you have cracks that originate from the ground up, that means you have a bad subgrade that you're building stuff on. So that's one application. If you're building an embankment and it's not as dense as it could be, it's loose, rutting, it can shear off. There's a plethora of different things that can happen. So,
right. Could a building collapse?
Absolutely.
Bridges, buildings can collapse.
Right.
That's what this is all about, really. It's finding out how to make sure as they build a structure, whether that be a bridge or a building, that the conditions are understood that they're building on top of, and then how to address any issues that may be there with the construction. Whether that's understanding how to get the soil to the right optimum moisture content to compact it. One thing that I've always described about the moisture content, if you ever go to the beach and you're walking from the road to the beach, you start walking across the loose sand dunes and you're struggling, your feet are falling in, and as you get close to the beach, all of a sudden you notice it gets hard. The ground seems hard, and as you get out into the water, all of a sudden you start sinking the soil again. That point, if you walk, there's places along the beach that if you go to the sand and you stomp your feet, you can't even dent it. And that's what we call an optimum moisture content for a soil, for sand, everything. Every kind of soil, clay has an optimum moisture content. A lot of the work we do revolves around understanding it's that and how to prepare soil to be. So when they haul soil in and they have to lay it out and compact it, we have to know what the optimum moisture content, and that's what Aaron's doing here. Is he's running a test on the soil to check and see what the optimum moisture or wet density or dry density of soil is.
And then y'all fix it if it's not ready to be built on?
We go out there, and as the contractors are working and placing soil on the ground, and they have compaction machines that we have devices, nuclear gauges that we place on the ground, and we can measure the density of the soil and make sure they're compacting it as they're working. And they'll bring it up in certain size lifts depending on the application. And we will test it along the way in the field as the work's going.
As the work's going. Okay.
And a lot of what we do too is also verifying that you're using the right type of soil to build on. So if they specify, hey, a lot of what you're going to see in the state is an AASHTO class system. It ranges A1, 2, 3, all the way to an A7. A1's really good material to build a road on. A7 is not material to build a road on. So there's different applications, but a lot of times the state will say, okay, if you're going to build an embankment, you can use A1 for A6, something of that nature. So we'll send it we'll classify it and send it back to basically justify whether or not it's appropriate for that material application.
And when you say an embankment, that's like the side of the road?
Slopes on the side of the road.
Yeah. So it's different soil for different types of construction projects.
Applications.
Yeah.
Yes. And then this is, and he said ASHTO, and I don't remember what ASHTO is, but we have what's called an ASHTO accredited lab, meaning you have to be accredited, gone through certain types of tests to prove your ability to run these types of tests.
Right.
We're an ASHTO accredited lab, so that's how the DOT uses us.
Right. So y'all are the first stage of any construction. Before we build anything, we got to check the soil out.
We used to be, as geotechnical engineering firm, the redheaded stepchildren. Right? They looked at it as no big deal, and as more knowledge grew, and even in the last couple of decades, they've learned that the first phase, the geotechnical component of understanding what you're getting ready to do and build, gives you the information that you need. And this whole lab is about understanding that process and giving engineers and architects and designers the information they need to build a building or build a bridge or whatever they're building. Build a dam.
Okay.
So a lot of times, like say for instance, you have a piece of steel that's repeatable, and when they manufacture it, you can have different types of steel, have books that tell you different properties on it. We define the properties of the material that's coming into the lab. Because even if you have an entire site that's the same material, you could dig a hole and then dig a hole 10 feet away from it, and it technically be something different. So
yeah, we have another machine over here that we pull steel with to just kind of confirm how it's going to act, what strength it has, and make sure it's being manufactured to the standards that it's supposed to be.
Right.
I'm interested in the clean room.
Yes, let's go look at that.
This is our clean room. It gets the name clean room basically because we want to minimize the amount of dirt that's exposed to it to mess up the fancy equipment. But as we look into it, a lot of this, to Glynn's point, has progressed exponentially over the past few years. So a lot of this, what you're going to see back here, are actually what we're going to call triaxial tests. And this used to be something that we ran manually. We had panels that we would check with, and now it's a fully automated system. So we not only are getting accustomed to working more effectively on the tests we perform, but also you have to keep up with the industry to make technological advances when they are applicable to see, okay, we can get this done faster, in a better format, whatever it may be. So that's just one example of it. All of these ticking systems, it's something where you used to have to look at a board, check pressures, and don't even want to go into that, because guess what? We have a fully automated system now. Now it's very critical that you do know the basics and fundamentals behind that, because if you don't know that, at a certain point you're just pushing buttons. But that's just one application of how things have been fully automated. But like I said, we've got a triaxial system. We have our direct shear system, which essentially, if you have soil that's together, what this is telling you is if you have a clay, it's going to be really slick back and forth. If you have a granular sand material like this, it's not going to be as slick. So basically what this measures is the friction that's occurring between the particles for the certain applications, whether they're using it behind a wall near a bridge or building a slope on it. But essentially, this will define the internal friction angle, basically the amount of friction that occurs between a material as well.
Do you need to be good at science to do this stuff?
So you don't necessarily have to be great, but it is good to have.
Okay.
And we use math every day.
Okay.
Do you necessarily have to care about biology or science? No, but it's great to know. Here's one thing, is that we've had plenty of people here who have learned along the way. It doesn't necessarily mean that because you're not good at it now, doesn't mean that you can't become. There's plenty of people who, don't have college degrees that come in and turn out to be way more phenomenal contributions to the lab than people who have 4-year degrees come in here and think they've learned stuff when in actuality they've learned just as much, which is nothing as much as the other person. So I would emphasize an interest in science. Yeah. It definitely makes the job better if you enjoy what you do, but it's something that if you aren't great at it now and you have a willingness to learn, that's a really important characteristic.
Right.
I think one thing to differentiate between what's actually going on in this area of our lab is going back, the other lab tests are more about, just like Teresa said, she really liked getting her hands dirty. There is some adding and, general mathematics is going on in some of that stuff. When you start getting over here, you're getting a little bit more into a more engineering realm. You probably need to be more advanced in that capacity. But it doesn't mean I used to work in the old versions of these. I used to put these remolded samples in these chambers whenever I was running the lab years ago. So it's not like you can't. I'm one. I'm just a high school graduate who worked his way up the ranks, just like you said. I've been here a long time, and I'm excited to see the changes that are going on in our lab.
What you're seeing here is this is actually what's happening here is they're running pressure through this and actually running to shear this material. So whether you can see it or not, it actually is filled with fluid. So it's actually a pressurized system. So the engineers specify pressures for us there's different deltas of pressures that we apply to the soil. And so what that'll do is not only does it also dually define the amount of friction within a material, much like the other one, but this is more for fine grain type materials for that. Because not only does it define the internal friction angle, this ultimately will also tell you the amount of cohesion, which aka is how much something sticks to one another as well. Both of those, the friction as well as the cohesion in a material, can be very critical properties, and that's what this is aiming to define. Basically how sticky it is and how much friction and how much resistance between particles within the material there is as well.
So at one point, y'all didn't have these machines doing this, and you were doing it by hand?
No, well, we had less automated. This is way more advanced than we ever had whenever, I'm talking 25 years ago, working in the lab. We still put them in the molds. We just had to actually control the dials to recreate the pressures on the sample. This sample may be a soil sample that keeps it from 50, 60 feet in the ground, and we're mimicking the conditions for that soil when it's in the ground down there. When they're maybe building a bridge and they need to drive piles in the ground, they need to understand what that soil is going to act like when they do that.
Right.
And maybe skin friction. Clay is more sticky, so when you push something into it, you get friction on the sides. They look at all kinds of data. So this is just mimicking the conditions of that soil where it was in the ground. Not necessarily every test, but this probably is.
Okay.
It's just really exciting for our company. We're a growing company. When I came here, we had probably maybe about 30 people. In the last couple of years, we've exceeded 100. And we've got multiple offices now down in Bluffton, here in Columbia. We've merged our Columbia offices here, and that's why if you walk through the rest of the building, it's empty offices as we're moving in the next 2 weeks.
So y'all have expanded threefold since you started. What do you think has helped y'all be so successful?
Well, one, I think I'm working for a company that cares. Be honest with you, and you know that. You know me well enough to know. I work with people that I really respect, that have a level of integrity, and are solution-based thinkers. And the one thing about our company is we still look at solving problems in every aspect, in the environmental realm or the geotechnical engineering realm or in the materials, where we become a part of a team for our clients. And I think that's really, we've continued to replicate that process, being there and solving problems for people and doing it effectively. And, as we've done it, some of the stuff that people who are listening right now, some of this may be a little confusing and maybe not necessarily clear. We're not trying to make it complex. It's some of it is, some of it isn't. But and that's the way we look to our clients too. So in the environmental realm, just like you was talking about Carolina Crossroads, I'm doing all the asbestos and lead testing for all the buildings they're going to tear down during that process. We have many aspects of that. We just our company is a good company. And we have good people who run it, and I think the people will understand that about us, and that's what.
Who are some of your major clients?
DOT is a huge client. We've actually, Alex has gone and worked in other areas of the state to manage labs for the DOT. And that's how we've kind of grown in this world. DOT, I do a lot of work for the University of South Carolina in the environmental realm. We also do some geotechnical work for them. And we have contracts with multiple counties throughout the state. Beaufort County, we have large contracts with them. Lancaster County, Richland County.
So a lot of government.
A lot of government stuff. But we have private clients too. And then, in my realm, in the environmental, I get people that call me off the street that are talking about their house and concerned they have lead or concerned they have mold. And they call me, and that's just somebody that's off the street living in a home. So it's just, I think we just happen to be a good company. I'm not going to critique anybody else. I think that's why. And we're just a good company, and we've grown and grown, and people appreciate a good company.
Yeah. Well, how long have y'all had these machines?
I think we got these before we moved in our Blanding Street office, so I'd say we had them up in operation. Would be a question for Alex. I know he had something come up. I had to walk away, but I think we've had these for at least 5 to 7 years, and then we had them kind of sort of set up. Now they're fully set up, and the automated component of it, what Alex was talking about, how this machine runs on its own. You literally had dials there, and I don't even see where we have the old stuff anymore. It's probably stopped. We probably sold it to somebody else who's coming up. Couldn't. I mean, that's a lot of investment for what you're seeing.
And does this save you time on your work?
Some of the tests you literally had to stand here and run the test.
Okay.
20 years ago. Now it looks like to me, and you tell me if I'm right, Alex. Now that you're back, and thank you for coming back. Because if you're going to be able to explain why this, I'm sure being able to walk away from this machine and have these tests going on without any involvement and a computer monitoring it and recording the data. We were literally having to record the numbers off a dial gauge. Now the machine is feeling the pressures, reading the pressures from the sensors, and it's controlling it. So you can walk away. Some tests you have to record some kind of data every minute.
Yeah.
Well,
and you just stand here all day.
Oh yeah. I remember. I don't think you can automate a hydrometer. I would say that not to tell y'all what that is, but I mean, standing there doing a hydrometer, I used to do this daily, and it was just you had to sit there. You might be doing something every minute, and it kind of graduates up to every 5 minutes, and then eventually you can walk away and do something else. Once you start some tests,
you're standing there for hours.
This looks like it was allowing us to walk away once it's set up and starts. You can walk away from it.
And at the end of the day, if I were to just say in general, I would say this is doubled to tripled our production rate.
Right.
So not only can you run something passively, which you do have to babysit to make sure, just because you press the button doesn't mean anything's going bad. Believe me, we've had where the computers have mysteriously reset over the weekend.
Start all over.
Right. So, but overall, there is a lot of analysis for the data, but I would say that it's probably doubled to tripled the amount of time that we have to use to actually run the test. Now there's molding the specimen, things of that nature, but actually being able to actively look at it, check on the pressures, like Glynn said, that's right out the window. So a big thing that I look on, I don't deal a whole lot with the triaxle portion of it. We actually have one of my coworkers, Rebecca, she specializes in this. She runs the darn show for triaxles, so I kind of give her the wheel on that. But it's an ongoing process. So anyway, I love automation, but at the same time, like I said, it's one of the things our owner always says is, so when we run a test, he doesn't want people to run tests that you don't know how to calculate the results. Because even if we're handing it off to somebody and they're calculating the results, he doesn't want us to just do step 1, 2, 3, 4. He wants us to know what we're doing so that as we're performing the test, we can actually sink in and it make more sense to us.
You may know what a piece of rebar is, but when you build things out of concrete, you don't just pour the concrete there. You may put steel in it, and you may put rebar in it, and they may be tied together inside the concrete. And if you've ever seen a building tore down, you'll see inside the concrete there's steel. The steel that goes in there has to be tested. So we have a machine over here. We'll show you that where we pull that steel and break it.
Okay.
So what you're going to see with concrete structures is they're going to consist of it's going to consist of concrete, but it's also going to have a metal skeleton. It's going to consist of rebar. We've probably seen these in one way, shape, or another. They complement each other. They're the yin to the yang to each other. So you've got concrete, which is very strong compressive-wise, where compression is squeezed down on a cylinder. It's strong for that property. Whereas with your steel, it is strong in a tensile property in a sense that its strength comes from you being unable to pull it apart as opposed to compressing it down. So what we actually do, show you guys the steel machine. We actually, for the tensile strength, we're taking steel and we are pulling it apart until it ruptures and hurts. And so what we do with that, we actually take the max load. So you guys have probably heard PSI before. PSI stands for
pounds per square inch.
Pounds per square inch. So we've got jaws right here. We almost started testing some yesterday. We couldn't pull off, but this ultimately will group the two. We've got jaws and clamps. We put it inside of this. This platen raises up, and we actually run this until the steel ruptures. So what we do with that is we take the max load. This actually can apply a load up to 400,000 pounds.
Jeez.
So what we'll do is we'll take the max load that occurred when it broke, and we divide it by the area. So the max load's in pounds, the area is in square inches, and that gives us the max tensile stress, which is pounds per square inch. So it all ties back to it. Same thing over here. We actually have our forming compression machine, and this is where we run our concrete tests. So this is once again something that has become fully automated over time. We used to just manually operate a pump, a hydraulic motor that would break these, but essentially we load a concrete specimen in here, and just like the opposite of that, where we're pulling steel apart, we actually squeeze these and compress the specimen until it ruptures. And that is the same exact principle. We take the max load in pounds and we divide it by the cross-sectional area in square inches. That gives us our max stress in pounds per square inch.
And does it make a big mess?
It can. That's why we've got a straight
But
jacket.
obviously, you guys are keeping this place clean, and I've got to applaud you on how neat everything looks over here.
We've got a stray jacket that we put around the cylinders. I just wish I had one for Glynn.
Wow. You can see all the top of the ceiling.
Yeah, this is a clean, no.
Moisture.
The sauna.
I'm trying to remember. And so we keep them in this environment until they're ready to break.
The cement.
So yeah, they break them at different times. Concrete cures over time. So, and depending on how it's being used, it may be used on forms, and they need, as a whole function construction, they may need to pull the forms off.
And what does it mean to cure?
That's what this is, the curing room. So you kind of keep a cylinder moist while it's curing. And concrete,
that means it's hardening.
It's liquid when they pour it, and then over time it starts to harden. And within the moments of being poured, it starts to harden. And as it gets harder, it gets strength, gets harder. But if you try to break it in 3 days, it'll just kind of crumble on that machine. And it'll give you some percentage of what the design. Going back to the aggregate, the stones we showed you on the table, you have a mixed design for concrete, and it's got a certain proportion with those components in it to give it, and a certain amount of cement to give it a certain strength. It doesn't get that strength right off the bat. It still has to cure. And so it's kind of like if you have clay and it sits there, gets hard, it gets kind of crusty hard, and over time it becomes this hard thing you can't even break. Concrete does that a little quicker probably, but we check it along the way to make sure they're not having a problem with the concrete in the field during construction. So they cure into this room, keep them, sometimes they submerge them in the tank, but we cure them and then we break them. And then take them out on that machine we just saw, and we break them. You know, compressor strength of that machine.
So if they were to use cement that hadn't cured completely, it could just crumble.
So if it goes back to water, you know, a mixed design will have a certain proportion of all the components. It will also have a certain amount of water that is acceptable within a certain range. The concrete comes out of a plant with the ability to add a little bit of water, but they'll have a maximum amount of water, because what happens over time is too much water, the concrete comes full of the mix. And most people in the construction industry are always going to put water in concrete, but we have to control it. We'll be in the field testing and making these cylinders and controlling the concrete truck drivers, making sure they're not adding too much water to it, you know, to make sure they stay within the design. There's criteria for everything we do in this, from the tools to the steels to the concrete. So you definitely don't want concrete to go bad.
I'm stirring up with a lime solution that helps the beams to hydrate. We actually have our upper beams, correct? We got a project coming up for Sumter County Airport where we're going to be breaking beams for flexural strength for the pavement. And so those are going to come in and stored here.
Yeah, we did that for a long time. On the Columbia Airport, Metropolitan Airport, the beam molds are around the corner, and we got a separate type of breaker that kind of teeters them on top of the piers, and then it pushes in the center and it fractures the beam. And when you're laying concrete down as a pavement, like for a taxiway or a runway for an airport, you still have to understand it. You still have to test the concrete, make sure it's designed and made mixed properly.
Wow.
And so we're just testing it in that capacity.
Okay.
In my world, I deal with environmental. So if you're already certified in certain things that I would need you as far as asbestos certifications or lead certifications, it may give you a better position. But I really don't know. Actually, I mean, you may come into the job and it may be a $15 an hour job. It may be, you may be qualified enough with all your certifications. You may come in at $20 an hour. I don't know about a lab technician and what kind of range
I'd say comparably for a starting rate, it would be something anywhere in the ballpark there for 15 to 20 or something.
Yeah.
Starting rate.
That's right.
Yeah. What kind of jobs could a high school graduate apply for?
You could apply. You could come work in my lab tomorrow if you're worth a darn. So,
okay.
Yeah.
Anybody who knows anybody, just let us know. But really, it's a lot of it's communication skills, things like that. So, I mean, we welcome just about anybody. Glynn, with that,
you maybe some mechanical aptitude in the concepts of handling the machines and assembling sieves and understanding that there are different sieves orders and being able to think about arranging the sieves in order depending on the particular analysis you're running and whatever they require for whatever kind of AASHTO level it's supposed to be.
What would a high school graduate do? What kind of things?
So introductory type stuff. I could ease you in and immediately the first day have you running some lab tests out here.
They're working along a bunch of people in the construction industry. And those jobs can move, that target can move. So the field inspectors, like I was talking about earlier, they may have to accommodate a concrete pour because of the weather, due to the high temperatures. They may want to pour that concrete to start at 4 o'clock in the morning. They may start it in the evening, or they want to do it all night. So, there are scenarios, but if he's bringing a high school student in here to work in this lab, it's probably going to be comparable to something like a 9 to 5.
We've got a lot of interns here that are at the university or things of that nature, and so they actually work part-time schedules. So really, we work around a lot of class schedules as well. So once again, we do have a lot of flexibility, but generally, I'd say 8 to 5. If you just want to take a basic schedule.
And 18 years old. Yep, 18 years old to work after high school.
Thank y'all for having us. We appreciate it.
Thank you.
Thanks.